Hi, I'm here with you today to talk about the Fundamental Theorem of Calculus Part 2. Now, understand please that the labeling of Part 1 and Part 2 is something that varies. It varies from book to book, from teacher to teacher. So we are just labeling it for our own internal purposes so we can reference these two related but kind of different in your brain ideas. So when you're referring to this on your AP exam or to someone, like if you have a friend at another school who's taking calculus, it's better just to call it fundamental theorem rather than specifying a number. Okay, so let's remind ourselves of what we call part one. What we call part one is when you're looking at a definite integral, and your integrand is some function of x, your bounds are some numbers, that we now know that we can find the exact area under that curve, under the curve f of x, from A to B by taking an antiderivative and substituting in our bounds and subtracting. And this is a stunning revelation, because why on earth would area be the exact reverse of finding slope or rate of change? That is sort of a remarkable fact. Well, let's take a look at Fundamental Theorem Part 2 and see if we learn any more about that relationship. So in this problem, it's really important in this setup to notice the notation. Okay, so this problem mentions that we're looking at a function of x, and yet I also see that x over here. Now that isn't really that stunning. I mean, most of the time when we have a function of x, we do see x in the equation somewhere, right? So that's not really that amazing, but it is unusual relative to what we see when we write out something like this, right? In this situation, my function of x is here, my bounds are numerical, okay? And so this is a slightly different situation that we are considering. Because the function is a function of x, there is this other variable. Now we know as mathematicians that it would be poor form to use the same letter to mean two different things, the same variable to mean two different things. So there's this other thing in here, this t, and that has a very unfortunate name. It is called the dummy variable. And it's because we really could put anything in that. It's really just like a placeholder. I could have, 3 alpha squared plus 4 d alpha, and the rest of the problem written out as it is, right? I call this f of x. And that would have the exact same meaning, it turns out. I could have 3 heart squared plus 4 d heart, and that would have the exact same meaning because this is a function of x. And so it's the x that ends up being of importance, okay? So that dummy variable literally could be anything. It is really, so we do not use x in two different places in two different ways, okay? So we're going to go through this. This is set up to be a dialogue, okay, between you and me. And so I am giving it as a monologue. And hopefully you are filling in your mind on your paper the rest of this dialogue. So the first thing says find an equation for the function capital F of x. Now I used a capital letter here just because we've been using capital letters to indicate antiderivatives, and that is what this is because we have an integration sign. We know that's going to be an antiderivative. I wouldn't have had to necessarily call it that, but I did. Okay, so I'm looking for an equation for that. So I'm going to write down my integral with my little dummy variable of t in it, and I'm going to utilize that first fundamental theorem because I have this feeling that math is generalizable, okay? And so even though I'm not really used to having a variable here, I'm going to just see if I can kind of make use of the situation where I had those bounds that were numerical. So I'm going to anti-differentiate. So antiderivative. Notice I'm using t's because that is what the dummy variable is. And then I'm going to use my notation that says, okay, I'm going to keep track of those bounds. The bounds are x and 2. And now I'm going to substitute in the bounds according to Fundamental Theorem Part 1. So x to the third plus 4x, and then I'd subtract. So if I put a 2 in here, let's say it's 8 plus 16. So minus 16, the minus because this theorem has subtraction. Okay, so great, that is a nice equation. This is indeed called f of x. So you can see through all of my links here, right, all these things are equal. So capital F of x is equal to that. The next part says find capital F prime using part A. So my eyes are going to be looking here. Capital F of x is this. So now if I need to find capital F prime, I'm going to have my eyes look here. This is what my piano teacher used to do when she wanted me to look at a part more closely. She would draw glasses with no eyes in them, just glasses. Anyway, so we're going to take the derivative of that. So 3x squared plus 4, derivative of negative 16 is 0. And then it said, did you notice anything? Well, this is one of those ridiculous teacher questions. Like, why would I be asking this if there wasn't something to notice? I mean, the answer is not no, you guys. The answer has to be yes. So I look here, and I look around my paper, and I notice this. It's the same, except the t became an x. So same as integrand at the beginning, except t is now x. Interesting. So now part C is wondering, would the answer in part B, the answer we just discussed, would that change if the 2 had been a 5? Well, let's think about where the 2 was important. The 2 was important back here, right? Because I had to plug in the 2, and then that's how I knew that this was minus 16. So that would be a different number if this had been a different number. But then I took a derivative, and the derivative of any number is going to be this big fat 0 right there. So I'm going to say no, because the derivative of a constant is going to be 0. Okay, I would have had f prime of x equals x cubed plus 4x minus negative, I'm doing math in my head, 145. Right, and then when I take the derivative, that would be gone. F prime would have been the same. So now the math. They're trying to get me to come up with math. So I'm going to pick a weird color. Let's see. What would be a good weird color? Maybe dark green. Okay, so draw a conclusion about that. Well, this is like what I started with, right? At the way beginning-ish. Well, at least part of it is. I shouldn't say all of that is. The part that's like what I started with is this. I had an integral, it had a dummy variable of t, I had bounds that were a constant, that's the a, and an x at the top. And then later on, I was asked to find the derivative of that. So if I include this symbol, it's really asking me about this step. And in that step, I ended up getting the integrand with x plugged in. So the way to say that is, here's my integrand f, and I'm plugging in an x instead of a t. Huh, that's an interesting thing to write. So the derivative of the integral is the interior function? Question mark? Let's look at this other example. So we have here something that looks sort of like the last question, but a little bit different because now we've got this. Okay, so there's still an x in the bounds, but there's more. There's a 2. I wonder what the 2 is going to do. Well, we have a strategy for sorting this out, so let's use it. So we have this problem. And fortunately, this integrand is one that I know the antiderivative for. That's the opposite of cosine. Keep track of my bounds. Use good notation. Then I'm going to plug stuff in. And plug plug stuff in. Okay, that was that. I mean, I could find out what pi over 3 is, I guess. Cosine of pi over 3, that's a half. So if you wanted to write plus a half instead, that would be fine. That would be better, of course. It's always good to do more math. That's actually not quite true. As I was saying that, I'm like, well, unless you're adding things together unnecessarily. Hate to lose an AP point for adding wrong. Okay, now we're going to take the derivative of that result. Okay, so this line up here, I should have labeled, that's capital F of x. So now I'm taking the derivative of that. So when I take the derivative of negative cosine, well, the derivative of cosine is negative sine, so negative is positive. So I'd have sine of 2x, and then chain rule, then the derivative of a half is 0. So this is 2 sine 2x is how I like to write it just for clarity. So now think about what we found out last time. We were like, oh, that matches. Look at this. Then look back up here. This kind of doesn't quite work, right? Like last time it was like just putting the x in. This time it's like putting the 2x in, but you got this extra 2. Why did we get the extra 2? Because of the chain rule. Because we were taking a derivative. Oh, that kind of makes sense. Okay, so here I'm going to say sort of that there's a chain rule element as well. So it's not going to be just put the x there, right? Remember last time we said with the more simple case, you just put the x into whatever the integrand was. This time, if you have something in the bound that's a more complicated function, not just a naked x, the x with blah, 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 that's going to end up going in the integrand. That part is true. But because of chain rule, you're also going to have to take the derivative of that interior function. That makes sense, because that's when chain rule even comes up, when you do composition. I'm so excited about this. All right. So that's our new result, my dears. Okay, so I think your copy, if I remember correctly from when I looked at this like 3 days ago, I'd like you to have the U on the top and the V on the bottom. I think I typed it the other way, but just because, for reasons. Okay, this is our fundamental theorem of calculus. Okay. So it is written here as generically as possible. So in our problems, our lower bound was a constant. But honestly, your lower bound could be a different function of x. And we also could have a constant. It doesn't matter. If we have a constant as, say, like this lower bound, like the 2 or the 5 that we discussed, then the rate of change here would be 0, which is why we didn't even see this part in our examples, okay? Because this rate of change was 0. But that is Fundamental Theorem of Calculus Part 2. I'm super, super excited about it, okay? If you did want to write it the order that it's in, right, it's this, okay? But tomato, tomato, okay? And I don't love the prime notation. I think it's way too easy to blow past seeing a prime, but, you know, your choice. I'd recommend using the Leibniz notation instead. All right, so now there are several questions to do, and I'd like you to just keep in mind the theorem that we just learned, and pause the video and come back and see if you're understanding. Check for understanding, okay? Try the 5 problems that are there. Okay, so the answers here show a long way, and then there's an implied short way. So we'll talk about both. But let's say that you just looked at this and said, all right, that's it. That would be totally fine, right? Because you'd be using the short way. You would say to yourself, so I see that I want to take the derivative of a function, and I'm taking the derivative with respect to x, and here's my independent variable x, right? That's important. So I'm taking the derivative with respect to x, and my independent variable is one of the bounds. So that means I'm using fundamental theorem part 2. And the shortcut is what we just found in those examples. I can just put that x into my integrand. The derivative of x is 1. The derivative of pi or negative pi, either one, would be 0. So this part is not even there, and I'm done. That's the short way. Now, should you ever forget and not be sure what you're doing, okay, then you wouldn't have this answer because you forgot, right? And so you could say, all right, well, the antiderivative of cosine is sine. Here are my bounds. I plug in my bounds. I take the derivative of my results. And guess what? You still get cosine. So should you forget, you can often, though not always, you can often still do the problem. Now, the reason I say often, not always, is because sometimes the integrand is something for which we do not know the antiderivative. Theorems would help in that case. All right, so we look at this, and that's what I was just talking about. Notice that we do not yet know the antiderivative for that yet. Notice how I said yet. Okay, so we don't yet know the antiderivative of that. However, we can still find the derivative of this function with the independent variable in the bound because fundamental theorem says plug in your x, the derivative of x is 1, the bottom is a constant, so it's not going to matter because when I take a derivative of a constant, I get 0. Done. This guy. Okay, so for this guy, we're going to need to take our bound, take this x squared, plug it in, and then because it's not just a naked x, we need to remember chain rule. Oop, that didn't work. There we go. So the short way is just doing this. The long way, if you chose to take it, would be, actually no, this is just explaining. Never mind. This is not the long way. I lied. Okay, yeah, so this is just showing plug in that x squared, take the derivative of x squared, that's 2x. Okay? This one, a little bit weird, right? Because you have the 5 on the top and the x on the bottom. So what I have printed here explains that you could choose to reverse the bounds and use one of your properties, right? You know that when you reverse the bounds, you just need to throw an opposite sign out in front. That is something you could do here. And then you could say, all right, I'm plugging in this bound, and it's just a naked x, so I'm good to go. You also could choose to not use that property and say, all right, when I substitute in this 5, then I'd have to multiply by the derivative of 5, which is 0. And then I would subtract, plugging in my x, and the derivative of x with respect to x is 1. And this is the same answer. Math works. The last question I asked you to do was one that had x's in both bounds. So for this one, I would think about plugging in my x squared into my integrand because I'm taking a derivative of an integral that has x in the bounds. Notice that this theorem is not about, like, if this weren't here, I would not be doing the same thing. It would be a totally different kind of question, okay? That's more like the integrals as functions situation, okay? This is the derivative of an integral where the independent variable is in the bound. Okay, so we're going to plug in our upper bound. We're going to think about what the derivative of that upper bound is. Then we're going to subtract because it's fundamental theorem. Plug in our lower bound. And the derivative of the lower bound is 2. Okay, so you could tidy that up if you want, but that's the scoop. Thanks so much for learning with me. Bye.